So in my last video, I talked about how to set up a computer cluster using desktop computers and a home wireless network. We went through several steps to set up this cluster, and just to recap what we have talked about in our last video, we talked about how to set up host names for the different computer nodes on our network. We talked about how to set up the secure shell or SSH so we can log in to the different computer nodes from other nodes. And we also talked about how to set up a shared file system or network file system, NFS, so that the different computers on the network can access files that's kind of shared by all the computer nodes. We talked about how to install compilers and the MPI library, and we did some testing. The computer network, the computer cluster we set up last time works fine, but its performance can be improved further. So in this video, we're going to discuss how we can actually make improvements on the performance of our cluster. So our cluster has two major problems. One is that the interconnection provided by the home wireless network is quite slow compared with a cabled network composed of switches and Ethernet cables. So in this video, I'm going to show you how we can actually improve the interconnection by changing from a wireless interconnection to a cabled interconnection using switches and cables. Another problem with our cluster is that the scalability of the file system is quite low, actually. And if you have a quite intensive I/O interactions in your computing job, if your computing job tends to read and write lots of files stored in your file system, the NFS won't be able to provide you the kind of performance you would like to have. And we're going to switch to a different file system that's called a clusterfs. There are several these kind of scalable file systems available in the open source community, and you can sort of Google. Lustre is another quite popular open source scalable file systems. clusterfs is quite new, and I myself have tried it, and it gives quite good performance on my small cluster. So let's look at how to improve the interconnection first. The target configuration we'll try to come up with, it looks like this. This is a kind of diagram, shows how the different components of our cluster is connected. So we have several computer nodes. In fact, I have two computer nodes, right? And those computer nodes are connected using Ethernet cable to a gigabit switch. And I'm going to show you pictures of a gigabit switch later, right? And then I have another computer, and we're going to use it as what we call the gateway. This gateway is also connected to the gigabit switch using a Ethernet cable. And it also connected to the internet, the World Wide Web, using a wireless connection, a wireless adapter that's connected to our home wireless network. So all the computer nodes do not have direct access to the internet, but it's going to share the internet connection with the gateway. So every time a computer node wants to access the internet, it's going to go through the gateway. And only the gateway is connected directly to the internet. For now, let's forget about the network disk storage for now. So the basic components that we're going to look at, one is the gigabit switch, the other is the gateway, and then the computer nodes are connected to the gigabit switch using Ethernet cables. So this is the picture of a typical Ethernet cable. It's called category 5E cable, actually. If you want to sort of Google, if you want to sort of look into the details about the configurations of this kind of cable, you can look into Wikipedia. And this kind of cable has a plug, has two ends. This end is called RJ45 plug, and it's some kind of standardization of communication of signals. And this kind of Ethernet cable is actually quite cheap. For a 7 feet long Ethernet cable, it costs about $2 on Amazon or Google Shops, and you can buy them without too much cost. So one end of the Ethernet cable, one of the RJ45 plug, has to go into what we call a switch. This is a picture of a quite big switch. I'm going to show you a better picture of a switch later, right? But you can sort of see lots of Ethernet cables are plugged into it. So that's one end of the Ethernet cable. And then the other end of the Ethernet cable goes into your computer. And this is actually a picture of a laptop computer with an Ethernet port on it. So you have the other end of the Ethernet cable that's plugged into the laptop's Ethernet port. And usually the Ethernet port is marked by this kind of symbol on a computer. So if you actually connect your computer, if you want to connect your computer to a switch, you use the Ethernet cable with one end goes into the switch and the other end goes into the Ethernet port of your computer. So here's a picture of two different kinds of a gigabit switch. This is a small one with just 5 ports. So on this small switch you can connect 5 different computers. And this is actually a big one. This one actually has 48 ports. So this one actually allows you to connect 48 computers together. And this one is a Netgear gigabit Ethernet switch. Right? And this one costs about $20 on Amazon, and you can find cheaper ones also. But Netgear is quite a good brand, and I myself use this one. But if you have more computers, you have to use a bigger switch. In professional clusters, they use large switches, large professional switches, and some of the switches are managed, which means that you can control and program its behavior by using software. And this one is actually a relatively big managed switch. So let's look at how I connect my computers. So this is the Netgear 5-port switch used at my home, and for now I have 3 computers connected into this switch, and this switch is powered. It's powered by the ordinary power cable. So the power cable is in the back, and then I have 3 Ethernet cables that's plugged into it. One of the Ethernet cable is actually connected to my gateway, and the other 2 are connected to my compute nodes, the other 2 computers. And this, I'm going to show you pictures of my gateway a little bit later. And you can see once the cables are connected and powered, the lights will come up, which means that this port is actually functioning correctly. So if you don't see those lights, which means that there might be problems with your interconnection. So the gateway must have 2 network interfaces. So this is one of the interface. That's my Ethernet port that's in the back of my computer, and you can sort of see my Ethernet cable actually goes into it and plugged into the Ethernet port, and the light is on. The other end of this Ethernet cable is plugged into my switch in my previous picture. Right? It also has a second interface, a second network interface. This is my wireless adapter. It's called Panel Wireless. This one works out of the box with my Ubuntu Linux operating system. I've been using it for quite a while, and it's plugged into just a USB port in front of my gateway computer. It's just an ordinary computer, but it has 2 network interfaces. One is the wireless interface that's connected to my home wireless network, and the other is my Ethernet port that's connected to my Ethernet switch. So now let's look at how do we actually set up this network on the software side, on the operating systems. So I'm gonna set up the gateway first. This is on my gateway computer. It's uh, some basic system information. It's Ubuntu 14.04. It's if you want to know about this particular computer, you can look at its configuration. It's Ubuntu 14.04 long-term support with some memory, and it's Intel Core i5 with 4 cores, Intel Ivy bridge, and it has 3.3 terabytes of disk space. And the name of this computer is called Gauss. I used this computer as a slave node in my previous video, but now I'm gonna use it as the gateway, of my cabled network. So my setup is gonna start with clicking here, and then what you want to do is to select the last menu item. It's called Edit Connections. I'm gonna click on it. So because this gateway actually has two network interfaces, one is the wired, which is the Ethernet port. The other one is the wireless, which is the wireless adapter that I was showing you in my last picture. So here I can see I have two different components. One under Ethernet is called wired connection 1, and one is under Wi-Fi. It's called lavender 1. So what I'm gonna do is I'm gonna select wired connection 1, and then click on Edit. So this will bring up the menu for configuring the Ethernet connection. So you can leave everything unchanged. The only thing that you have to change is under IPv4 setting. IPv4 stands for IP version 4. So if you go there, and then you have a selection that's called method, and if you click on this down arrow, you have a bunch of selections that's called let's start with automatic DHCP address only, manual, link local only, shared to other computers. What you want to do is to select shared to other computers, and then you're basically done. All you have to do is to click on save, and then that's it. But I'm not going to click on save because my connection is already set up, so I'll just click on cancel. Right? But you should click on save if you haven't actually set up the gateway yet. Right? And you don't really have to change your Wi-Fi connection, your wireless connection. Right? But if you want to look at the settings, you can also go to choose the lavender 1, my wireless connection, and then select edit. It's going to show you the Wi-Fi connections, the wireless network ID at my home. It's lavender, and then choose the mode of the infrastructure. Right. Wi-Fi security, you have a password that's typed in there. IPv4 automatic DHCP. Basically, your configuration for the gateway is completed now, but we still have to keep record of two very important numbers. I'm going to close this window, and then I'm going to go here, and then what I'm going to do is to select the second item from the bottom of the drop-down menu. It's called connection information. So under the connection information, you have two different tabs. One is called wired connection 1, which is the information for your Ethernet connection, and the other one is called the lavender 1, which is the information for your wireless connection. So let's look at the wired connection 1. Basically, under the general tab, you have some information about the Ethernet connection, the Ethernet port that you are having, the interface. It's Ethernet ETH0, the hardware address, which is basically the MAC address that I was talking about in my last video, and it's telling you the speed of the connection. It's basically the speed of the port. It's the maximum speed it supports is 1 gigabyte per second. Right? Securely none. And then on the IPv4, you have several things that's quite important. The first thing that's important is the IP address of your gateway. That's 10.42.0.1. You have a broadcast address, which is an address that's used for broadcasting information within your network, which is not something that you want to sort of change. It's sort of configured by the system. You don't really want to change that. And then you have a subnet mask that's 255.255.255.0. So in order to understand what's actually the IP address and a subnet mask, let's look at this particular PowerPoint slide. So let's look at this slide. I'm going to close this one, and I'm going to show you a slide that I prepared earlier. It's explaining what's actually the IP address. So every computer that's connected on the network has an IP address. If you want to use it to access the internet or local area network, it has an IP address. So this is one example of an IP address, which is the IP address of our gateway. It's 10.42.0.1. And it's composed of 4 different numbers separated by dots. Those different numbers are called octets. So it's basically 4 different octets separated by dots. And those different octets actually has meanings. Some of the octets actually is an ID for the network that you belong. For this particular case, the first 3 octets belongs to the network ID. And the last octet is the host ID. So how do I tell which part of the octets are network ID and which part of the octets are host ID? I look at the net mask. So if the net mask looks like this kind of thing, it's 255.255.255.0, which means the first 3 octets gives me the network ID. So I have a network ID that's 10.42.0. And if the last number in the net mask is 0, which means the last number in the IP address, the last octet, is actually a host ID. So my host ID is 1. So basically every IP address has these 2 components. One component is for the network ID and the other component is for the host ID. And in fact, all the IP addresses are classified into 3 different categories: Class A, Class B, and Class C. So for Class A IP address, your network ID is composed of just the first octet, because only the first octet in the net mask is 255, and the rest of them are just 0. So for Class A, only the first octet in the IP address belongs to the network ID, and the rest of 3 octets belongs to the host ID. And the range of the first octet for Class A goes from 1 to 126. And 10, this 10 dot something is actually reserved for private network, the local area network. And 127 is also reserved for special purpose, which is called a loopback. So if you look at an IP address that starts with 127 dot, then it's pretty much for it's reserved for loopback. It's kind of a interface that it's an IP interface, a network interface that the machine used to identify itself. So it's used by many networking utilities. And for Class B, the first 2 octets is for the network. And the range of the first octet goes from 128 to 191. And for Class C, the first 3 octets are for network. So the IP address of my gateway is actually belongs to a class C IP address because it has 3 octets, belongs to the network ID. So, and 192 is another number that's reserved for private or local area networks. So I hope this very simple or very brief introduction about IP addresses can give you some idea about what's the meaning of a particular IP and what's actually the meaning of a net mask. And if you want to know more information about how IP addresses are sort of designed and used in practice, you can again Google and look into the Wikipedia pages. So let's look at the connection information again. Right? So now 10.42.0.1 is the IP address of my gateway, and then the net mask for this particular network, for this particular IP address is 255.255.255.0. It's so the first 3 octets are for the network ID. If you want to look at the information about my wireless connection, it's telling you the interface, the hardware address, the MAC address, but the connection speed is a lot lower, you see. It's 108 megabytes per second compared with 1000 megabytes per second. It's a lot lower. It has some kind of security. And it also has an IP address, 192.168.0.107. And it's also a class C. It's also a class C IP address. So I'm gonna close it. So the next step is to set up the IP address on my compute nodes. So we'll look at a different computer later on. Now let's look at the configuration on one of the compute nodes. And I am on one of those computer nodes, and let's look at the information about this particular computer. I'll go here and let's look at this information about this computer. Ubuntu 14.04 long-term support, and some hardware information, and the device name is Fresnel. I have used this particular computer as the master node in my previous video, but now I'm going to use it as a compute node. So to set up the network configuration on a compute node, I'll click here, and then again edit connection. That's the last item on the drop-down menu. Under this in this menu item, in this dialog box, I have 2 items. One is called Ethernet, the other one is called Wi-Fi. But you can see that the Wi-Fi connection was made 1 month ago. So at this particular point in time, I don't really have a Wi-Fi connection on this particular compute node. It's the only connection I have is a wired connection. It's connected 3 minutes ago, and if I want to look at the details of this wired connection, I select this wired connection 1, and then click on Edit. It's going to give me this Edit wired connection 1 dialog box, and many tabs that I can sort of configure. I'll leave everything unchanged, but I'm going to change IPv4 settings. So under the IPv4 settings, I'll choose the method manual. I'll use a manual as the method. And then under the address box, I'm going to assign a IP address for this computer node. So what I'm going to do is that, so this particular computer node belongs to the same network as my gateway computer. So I'm going to the network ID for my local area network is controlled by the first 3 octets. So I'm gonna use the same 3 octets as my gateway for the first for the first 3 octets. It's 10.42.0, but it's a different host. So I'm gonna change the host ID. The host ID is the last octet. So I'm gonna change it to 3. So if you remember, my my gateway IP actually has a 10.42.0.1, but for this compute node, I'm gonna give it a 10.42.0.3, and then the net mask is identical to my net mask for the gateway. And then there's a particular field that's called gateway. And in this field, I'm going to give the IP of my gateway computer. That's 10.42.0.1. And then that's it for this address box. And then for the DNS server, I'm going to give the address, the IP address of my gateway. It's 10.42.0.1. And then basically that's everything that I need to change to set up the connection on my compute nodes. So once you're done, you click on save. But in my case, I'm not going to change my configuration, so I'll click on cancel and then close. If you want to know the information about your particular connection, you can click here again and then choose connection information, and it's showing you have a wired connection. You don't have a wireless connection tab here, right? It's different from the gateway connection tab that we looked at before. It has just a one connection. That's a wired connection, one default. It's under the general. You have an interface, you have a hardware, the MAC address, the speed of connection, 1 GB per second, and then you have IPv4. The IP address is 10.42.0.1.3, right? It's the IP address that you entered in that address dialog box, right? Broadcast address, that's configured by the system. You don't want to change it. Subnet mask, it's the same. It's identical to the subnet mask on your gateway computer. And then you have a default route. It's 10.42.0.1. That's your gateway IP. And then primary DNS, that's 10.42.0.1. That's again your gateway, the IP of your gateway computer. So you have to repeat the same process on all the compute nodes, but you have to give every compute node a different IP. All you have to do is to keep the 3 octets at the beginning identical to 10.42.0. Just to change the last octet. If you have another compute node, you can change the last digit, the last octet, maybe to like 5 or to 69 or 10 or any number that's between 1 and 255. No, not between 1 and 2. It's between 2 and 254 actually. So 255 is actually reserved for the broadcast address, so you cannot use that. But you can use any number that's between 2 and 254. You see, and then you're done configuring the network connections. And now we have finished configuring our network connections. We can try to test the connection speeds. So what I'm gonna do is that I'll try to connect from the gateway to 2 different computers. One is on my wired connection, which is Fresnel, and has an IP that's 10.42.0.3 that we just configured in my just a while ago. And I'll also try to connect from my gateway to a computer that's not in my wired connection network, but it is in my wireless connection network. So we can see the speed difference for different types of connections. The utility that I'm going to use for testing the speed is called iPerf, and it's quite simple to use it. And if you are not familiar with this particular tool, you can do in a terminal, you can do man iPerf, and it's going to tell you how you can actually use this utility to test the speed of your connections. So in order to test the speed of the connection, you need 2 computers. One listening computer, the computer that's listening to the incoming traffic, and also another computer that's generating the traffic. So on the listening computer, you type iPerf-s. That's gonna start the listening process, and then on the traffic generating computer, you type iperf-c and then followed by the IP address of the listening computer, and it's then this utility is going to print out the connection speed. So if you don't have this particular utility installed on your system already, you can do sudo on a Ubuntu operating system. You can do sudo apt get install iperf, and then it's going to automatically install this particular utility for you. So I'm sitting on my gateway computer, Gauss, and I have two terminal windows that's open. So I have two terminal windows. I'm going to use the terminal window on the right to connect to my compute node, which is Fresno, and it has an IP address that's 10.42.0.3. So I'm going to SSH to my compute node, Fresno. And then on Fresno, I'm going to start listening. So I'll do iperf-s. So it's showing you that server listening on TCP port 5001. Right. And then on Gauss on my gateway, I can generate the traffic by doing iperf-c followed by the IP address of my compute node, which is 10.42.0.3. And then it's gonna try to generate some data and transfer it to Fresno. Let's just wait for a while and see how fast the speed is. So the speed is about 934 MB per second, and it has transferred 1 gigabytes of data. So this is the speed for my wired connection, the Ethernet cable connection. So now let's try to connect to a computer that's not on my Ethernet connection, but it's on my wireless connection. And the IP address for that computer is 192.168.0.104. So in your case, it could be a completely different IP address, but it doesn't really matter. It's just for speed testing. And this computer is not in my wired connection, but it's in my wireless connection. So the gateway is supposed to be able to connect to the outside world, and it should be able to detect this computer on my wireless network. Again, let's look at what's actually the speed of the connection. So it's about 6.87 MB per second, and it transferred about 8.5 MB. So you can sort of see the difference in the transfer speed. You see, it's more than 2 orders of magnitude. That's about more than 900 for the wired connection. It's less than 10 for the wireless connection. And another problem with the wireless connection is that it's not very stable. So the speed can vary. So if I try to make the connection again to the computer on my wireless network, it's probably going to give you a different number. So this time it's 5.37 MB per second, right? It's even less. But for the wired connection, the connection speed should be quite stable. So if I try to connect to the compute node again, let's see what's actually the speed for this particular trial. Again, about 934 MB per second, right? So when we are doing high performance computing, we would prefer this kind of a high speed connect provided by Ethernet cables and switches, right? Especially if you are actually transferring a large amount of data among computing nodes. In this kind of case, the interconnection speed is particularly important, and you don't want to rely on a wireless connection that's not so stable and quite slow. And the Ethernet cable connection coupled with the switches, a very fast switch, should be the preferred choice. It can improve the performance of your parallel computer programs by quite a bit especially if your computer program is using the interconnection to transfer lots of data among computing nodes. Now let's look at how we can actually improve the performance of our file system. In my last video, I built a shared file system using the NFS or network file system. What I did was that I installed the NFS server on one of the computers I had. It was Fresnel, I think. So I was using the Fresnel as the file server, and then I installed the NFS client on the other machine that I had. It was Gauss, so I was using Gauss as the client, and then I exported a certain directory on Fresnel on the file server by editing a particular text file. It's a etc exports. I think it was a text file. So I exported a certain directory. That directory was called NFS under the root directory. I think it's I exported the NFS directory on the server, and then all I did on the client was that I mounted that remote directory as a local disk partition on the client, and then I can read and write files into that shared directory, which is NFS. And it was a relatively straightforward setup. I have just one server which stores all the file locally on its hard disk, and then there is a client. If the client wants to access a certain file, say file 1, it's going to generate network traffic through the interconnection. In my previous video, I was using a wireless interconnection, so it was quite slow. But that problem can be fixed now by using a cable and switch-based interconnection. It works, but its performance may not be ideal. The reason I'm saying that is, suppose you have a situation that looks like that. I have not just one client, but many clients, but I still have just one file server that stores all the files. So if all the clients are trying to access or read and write a certain file on the server is going to be really busy, and the read and write speed for each of the client is going to be really low, because all those different clients are going to be share a very limited amount of bandwidth through the cable, through the interconnection. So this is not really a very scalable design, especially if you have many clients that are trying to access a certain file on the server simultaneously. And what we would like to have is a certain setup that can scale to many file requests, and the kind of request and the load for file access is kind of balanced over the whole network. So a better design of this kind of shared file system is to distribute the entire file system over the entire network. So instead of putting all the files on just one server, we can distribute them onto multiple servers. So in this particular diagram, this machine actually stores file 1, this machine actually stores file 2 and 4, and this machine stores file 3. Right. Some of the machine can act both as server and a client, because it can request files stored on other remote machine. And of course, some of the machine can act just as server, which means that it won't request files that's stored on other machines. And some machine can act just as a client, which means that it won't store anything that's going to be requested by other people or other machine. So in this kind of situation, suppose the client wants to access file 1, then it's just going to access this particular machine. If you have multiple clients, for example, if this client this machine acts as a client. This machine also acts as a client. This machine requests file 2, for example. Then it's going to go to this machine. And this client is going to request for file 1, for example. And then it's going to go to this machine. So the load, read and write I/O load, is distributed over multiple computers. And this kind of distributed file system can be implemented very efficiently on the Linux operating system, and people have done that work for us. And here is a table of the currently available distributed file systems. This is a table that I grabbed from Wikipedia, and you guys can look into the page by yourself. It's comparison of distributed file systems. The majority of those are actually open source, except for this one. This one is proprietary, but all the others are actually open source, more or less open source. I think it's. So those open source file systems are freely available, and you can actually try them out. For example, Lustre are used in many of the professional clusters. Some of them are actually in the top 500 or top 500 benchmark. In the following example, I'm going to use GlusterFS, and the GlusterFS is currently maintained by Red Hat, the big Linux company. Actually, but it's still open source, and it's freely available. And there's also a Wikipedia page for GlusterFS if you want to look into the details about this particular file system. So in the following video, I'm gonna sort of try to install GlusterFS on my computers and try to construct a shared file system using this particular file system. And then we are gonna compare the performance of read-write performance of this GlusterFS file system with the NFS that I constructed earlier in the last video. So now let's try to construct this GlusterFS file system. I'm sitting on my gateway Gauss, and I have two terminal windows open on Gauss, and I'll try to install the Gluster file server on both Gauss and Fresnel. So both Gauss and Fresnel, these two computers are going to act as servers. In fact, both of them are going to be both servers and clients, actually, because they will also request files from other servers. So I'm going to use the right terminal to access Fresnel. So I'm going to control Fresnel from Gauss here. So I know that my Fresnel has an IP address at 10.42.0.3, I think it's. So now the right terminal is actually on Fresnel, and you can see the name of the machine. So the first thing we're going to do is to format a hard disk. We're going to format the hard disk using a particular file system that's called XFS. It's a certain file format. It's called XFS. And if you are not familiar with this particular file system, you can Google about it. One of the most popular file system on file format on Linux operating systems is ext4, I think. But XFS is a file format that's suggested by GlusterFS. So we're gonna try to format our hard disk using the XFS file format, and this XFS file format and all the programs that's related to it can be downloaded using apt-get. So if you want to sort of use the XFS file format and you don't have those XFS related programs installed on your computer already, you can do this. You can do just sudo apt-get install XFS prgs, so so it's telling me that on my machine XFS Pros is already the newest version, but if you don't have it installed already, this particular command is gonna install it for you. And once you have installed this package, you will have a command that's available to you, and it's called mkfs.xfs, I think. So this particular program is under my SBIN. So the first thing that we're going to do is to format my hard disk using mkfs.xfs. So what I'm going to do is to do sudo mkfs.xfs-I size equal to 512. And then my disk on Linux operating system, how do we actually manage and format hard disks? We'll talk about those issues in a separate video. But for now, let's just on this particular computer, I have an external hard drive that's connected to my gateway through a USB 3.0 port, so it's quite quick. And this disk is under DEV SDB 1, I think. Is it SDB 1? I hope it is right. Otherwise, I'm gonna sort of destroy my hard disk. Oh, it's telling me that the hard disk is already containing a XFS file system. So if I want to overwrite the existing file system, I'll just enforce it by using -F. So I'm gonna force formatting this external drive. So now it looks like it's working. So it's basically formatting my external hard drive, and it will take a while, I guess. And this external hard drive is 3 terabytes large, and I connected it to my gateway using a USB 3.0 cable, and now it looks like it's done already. So I have finished formatting the hard disk. Now the next thing we'll have to do is to try to mount it. So I have formatted DVSDB1 as a using the XFS file format. Now I have to mount it to a certain directory. So what I'm going to do is that so I have a directory that's created already. It's under srv sdb1. So I'm gonna mount my new disk to this directory. So what I'm gonna do is to do sudo mount sdb1 to this particular directory, srv sdb1. So now this disk has been mounted at this particular directory, and then I'm going to create a directory. I'm going to create a subdirectory underneath this directory. So what I'm going to do is to do sudo mkdir srv sdb1 brick dir. So now if I look at the directory, I have a brick subdirectory underneath my srv sdb1, this mount point. So for Gluster-FS, a basic storage unit is called a brick. A brick can be a certain disk or a certain partition of a certain disk, and the entire file system is made up of many bricks. and those bricks can be distributed on many different computers, or one computer can have several bricks, and um, several computers can share a certain brick. So the basic cluster FS is composed of uh, many storage units that's called brick. So on Fresnel, I also did the same thing. I also have a external hard drive that's 4 terabytes large, and I have connected this external hard drive to my computer through a USB 3.0 port. And that hard disk is under DV SDC1, and I actually have formatted SDC1 using XFS also, and I have already sort of mounted this particular disk at SRV SDC1, I think, and this this mount this directory also has a subdirectory that's called brick. So I pretty much did the same thing as what I have done on Gauss, except that it's carried out on Fresnel. So so for now I have two bricks. One brick is on Gauss on my gateway. It's under SRV SDB1, and then I have another brick that's that's on Fresnel. That's on my computing nodes, Fresnel, and it's under SRV SDC1. So the next thing that we're going to do is to install the cluster file system and also all the tools that's related to the cluster FS on both computers. So now let's try to install it. The cluster FS, the installation of the cluster FS has some slight difference from the installation of other software that we have done so far. It requires us to add a certain PPA. It's called a personal package archive. We'll need to add a certain PPA to our software repository first before we can actually download and install the particular file system. So what are we gonna do is to first add the PPA to our repository, and the command for doing that is sudo apt-get. No, it's not apt-get. It's add apt repository PPA colon cluster FS. I think the latest version is 3.6. I think by the time I'm making this video, they have a 3.6 version. So and then the next thing is that we have to update. We have to do a sudo apt-get update so that the change can take effect. And then all I have to do is to sudo apt-get install cluster FS server. So it's telling me on this particular machine cluster FS server is already the newest version, so I don't really have to sort of reinstall it. But in your case, this command is gonna sort of install this cluster FS server for you automatically. And on Fresnel, basically we have to repeat the same step. We have to add the PPA to the repository first by using sudo add apt repository, and then followed by the PPA for cluster FS, and then do a apt-get update, and then do a sudo apt-get install cluster FS server. So basically we have to repeat the three commands on all the machines that's gonna act as servers. And And basically that's all step that's needed in order to install the Gluster FS package. Now the next thing is that we have to create a Gluster volume. So a volume is basically a collection of bricks. What I was telling you is that brick is basically the smallest unit of is the smallest storage unit, and then a volume is a collection of bricks that could be distributed through the entire network, could be distributed on multiple uh, computers. So we're going to create a volume, cluster file volume, that has two bricks. One brick is on the gateway, the Gauss, and the other brick is on Fresnel, that's under SRV SDC1. And then we're going to create a volume that contains these two bricks. So now let's try to create the cluster volume. And before we create the volume, let's try to do a peer probe between the two machines actually. So let's try to probe Fresnel from Gauss first. Let's do sudo cluster peer. Let's probe my Fresnel's IP is 10.42.0.3. I think. So let's probe this one. So it's telling me probe success. So which means that from Gauss I can access Fresnel through cluster peer probe. And let's try the same command on Fresnel. Let's try to probe Gauss from Fresnel. So let's do sudo cluster peer probe. And Gauss has the IP that's 10.42.0.1. So it can see Gauss also. So now let's try to construct the volume. Constructing the volume, the command for constructing the volume needs to be done on just one of the machines. So I'm gonna do it on the on Gauss. So I'm gonna do sudo cluster volume create. I'm gonna call my volume. I have to give the volume a name. I'll call it GV0. I'm gonna call it GV0, and then set up the transport TCP, and then I'll give a list of all the bricks that's gonna make up the volume, and the bricks are gonna be specified both by the IP address of the machine and then followed by the directory on that machine. So the first brick is gonna be on my local host on Gauss, and Gauss has an IP that's 10.42.0.1, and then colon followed by the directory that I created the brick. It's SRV SDB1, and then brick. And then my second brick is on the other machine that's 10.42.0.3. That's Fresnel, and then colon. And I have created the brick under SRV SDC1, and then brick. So it's telling me that I have successfully created a volume that's called GV0, and then I'm gonna start the volume. So typed the wrong command. I think that cluster volume start GV0. I think it's okay. So it's telling me that I have started this particular volume, right? And so now let's try to mount it. Let's try to mount the volume onto a certain directory. And so before I do that, let's try to start the cluster file server service. So the command for starting the service, cluster fs service, sudo service cluster fs server start. So it's telling me it's already running, but let me see if Fresnel is also running already. Sudo service cluster fs server start. So it's also telling me it's running already. So now let's try to sort of mount it at a certain mount point. And the command for mounting the cluster volume is called mount.clusterfs. So what I'm going to do is let me see if I have a mount point. So I have a mount point. I have a mount point that's created already. It's a mnt gv0. So I'm just going to sudo mount.clusterfs. So I'm actually mounting. It's a local host, so I can actually. So that's 10.42.0.1. That's the IP of Gauss. So I can just replace this sequence with localhost, and then I'm gonna mount it. I'm gonna mount the GV0 volume that I just started to MNT mount GV0. So and now if I and then on Fresnel I'm gonna do the same thing. It's gonna I have to sort of mount it sudo mount cluster fs 10.42.0.1 GV0 because GV0 was created on my gateway Gauss, so I'm gonna have to sort of mount this remote volume to my local directory. That's mnt GV0. It's telling me it's already mounted on GV0, so we can sort of take a look at what's actually the content of this volume. This is on Gauss GV0. So it's telling me I have a bunch of files on it, right? And then if I look at, if I'm on Fresnel, I can also look at what's actually the content of this same set of directories actually. So if I want to sort of delete one of the directories, so if I want to delete one of them, so rm, I'm gonna do rm rf temp gv0 temp. So that directory has disappeared, right? Is it also true on Fresnel? Yes, I think it's also true on Fresnel. And so let's try to do some testing. Let's do some read and write test. So what I'm going to do is that I'm going to go to mnt gv0. That's the new volume that I have created. I'm going to read and write. I'm going to write a big file. I'm going to write a 5 GB file. So what I'm going to do is to do sudo dd. Now I don't really have to do sudo. I think I can just do dd. I think because I own this directory. I don't really need the root direction. So the input file is going to be dv0. So I'm going to use dv0 as the input to dd. And then I'm going to write out a file that's called a speed test. Basically, I'm dumping zeros into the file that's called a speed test under the current mntgv0 directory. That's my shared volume on multiple computers. And then the block size is 10 megabytes, and I'm going to write 500 of those blocks, and conv equals to f data sync. Sorry, I forgot the equals. So let's just to see how fast it can be. So I'm writing 10 megabytes per block, and it's writing like 500 blocks. So it's a file that's the speed test file. The output file is going to be about 5 gigabytes large. And let's see what's actually the speed. So it's telling me that it's getting 165 megabytes per second. It's not super fast, but it's still quite fast. So this is on cluster FS, right? So let's try to do that on the NFS system that we constructed in my last video. So that NFS is here, I think. there's nothing in it. Let's just repeat the command, exactly same command. I think let's give it a try, and let's see how fast it is. So the file size is about 5.2 gigabytes, and it took about half a minute to write 5 gigabytes of file on the cluster FS. And the average speed, I think it's 165 megabytes per second on the cluster FS. So let's see how long it's gonna take on the NFS that we constructed last time. And it's exactly the same setting. I'm writing zeros to the speed test, but this time I'm actually writing it onto the ordinary NFS, and it's a 75.9 megabytes per second. And the interconnection is exactly the same. Actually, it's all cabled for both tests. The interconnection is both cabled and a switch-based interconnection. So there's no wireless involved in it. So the connection speed is should be the same for both tests. But you can sort of see the speed difference is actually quite large. So for the NFS, writing 5.2 gigabytes of file took more than 1 minute actually, and the average speed is 75.9 megabytes per second. Right? And this is on Gauss, my gateway. So let's give it a try on Fresnel. Let's give it a try. So it's let me go to the cluster FS. So the speed test, this particular file was generated on Gauss using that dd command. So let me delete it. Let me delete it first, and then let's just repeat the same dd command. And then bs equals to tmm, right? And then count equals to 500. COMV equals to f data sync. Just see how long it takes. So if you want to take a look at the basic information about your cluster FS file system that you just cluster volume that you just created, there's a command for it. It's called cluster. So cluster volume info, and then followed by the volume name. So it's basically telling you the information about this particular GV0, this volume. And the name, the type is called distributed. There's another type that's quite useful, that's called replicated. So you can basically use your cluster file system as a kind of a backup. You can just sort of duplicate everything that's that you are storing. So you can use it as some kind of backup storage. And then the status has started. It has some kind of ID, a very long sequence. It has 2 bricks. You see. There's 2 bricks. Transport type is TCP, so it's basically a cabled network. And then you have 2 bricks. One brick is on Gauss, and it's under this directory. And there's another brick that's on Fresnel. That's the IP of the Fresnel under this directory. So some basic information about the cluster file system can be displayed by using this command. Right. And this test has finished. So It gives 114 megabytes per second. It's not as fast as on Gauss. I suspect this speed test, this output file has been written onto the local storage on the Gauss, I think. So how do you actually take a look? How do you check that? Right? How do you check that? So this is my volume. I can see speed test, right? But where's the brick? Where's the brick on Gauss? The brick on Gauss is under SRV. SDB1 brick, I think. You can look into it. So you see, speed test is displayed under SRV SDB1 brick. You see. So, but if you actually look at the brick on Gauss, where is that brick? SRV SDC1, I think, and then brick. And it doesn't have that speed test. You see, it doesn't have that speed test file that I just created. So the speed test has been stored locally on the gateway computer, the Gauss, right? And Fresnel was actually accessing that remotely through the network. So that's why the speed is actually lower, right? But it's still faster than the NFS. Actually, it's still faster than NFS system. Right? And during this process, we have to mount several disks, right? We did that through the command line. But if you have to restart your computer and you want to automatically mount those disks at a fixed location, you can put those mount commands into fs tab, I think. So if you look into my fs tab, etc fs tab, actually, it has a line for automatically mounting my external hard drive to this particular mount point. You see, so I'm actually mounting DEV SDB1, that's my external hard drive, to this particular mount point using XFS as the file format, right? And this is on Gauss. On Fresnel, I have to automatically mount SDC1. Actually, I have to mount SDC1 to my. So if you look at my, etc fs tab, you can see this line. I'm mounting SDC1, my external hard drive on Fresnel, at this particular mount point with XFS as the file format, right? And I also have another line that's actually automatically mounting the cluster file volume to MNT GV0, actually. So this can also be mounted. This cluster file system can also be mounted automatically every time you restart your computer, right? Here is a short summary about what we have talked about so far in this video. We talked about how to improve the performance of our cluster. So we spend most of the time talking about improving the interconnection among different computing nodes. And we talked about how to improve the scalability of the file system. That's the shared file system used by all the computing nodes. To improve the interconnection, we switched from a home wireless internet network connection to a cabled interconnection using Ethernet cables and switches. To improve the scalability of the file system, we adopted a scalable open source file system that's called cluster.fs. We installed it on our computers and we tested its performance compared to the one server, one client version of the NFS that we installed in my last video. So there are lots of ways to actually improve the overall performance of a cluster, and those professional clusters and those big companies like IBM and Cray, that produces those professional clusters actually put lots of effort to optimize its overall performance, to optimize the interconnection, to optimize the file systems, and lots of other things. So this is actually a picture of the back of a small-sized professional cluster, and this is a picture of the front, and this is actually a picture of one of the nodes of the computing nodes of the cluster. It looks very different from a traditional desktop computer, right? But in principle, it's actually quite similar. So if you actually compare it to a traditional desktop computer, it looks very different, right? Because the traditional desktop computer has many peripherals, like the monitor, the keyboard, printer. All those peripherals are not directly related to computing, so those peripherals can be actually removed if you are actually using if you are in a cluster setting. So this is actually the essential components of all the computing components actually. So all you need is this kind of hardware in order to actually carry out the calculations. So people can actually build this kind of a computing nodes in a very small box, and then they can stack them. Together. So in a rack, you can put lots of computing nodes, and you can control all those computing nodes from just one master node by doing SSH. So all you need is one monitor, one keyboard, and that's connected to the master node, and then you can control all the computing nodes that's on the same network. And so it involves lots of work to actually optimize the performance of a cluster, and not just on the hardware side, but also on the software side. So if you want to improve the performance of the interconnection, you can improve the hardware by using, for example, InfiniBand, by using 5-dimensional torus, 6-dimensional torus, that kind of a very good hardware. And also you can improve the performance of the message passing library. For example, right, we installed a message passing library on our Ubuntu, on our Linux desktops last time in my last video. Right, you can try to a message passing library is actually the software library that allows you to communicate among different computer nodes, and you can also try to improve the interconnection by improving the performance of that software library. So that also involves lots of work. And so in my past two videos, we have used lots of the command line of the Linux operating system. And for people who are not exactly familiar with the Linux command line, these may look very intimidating. So in future videos, I'll try to sort of talk about how to use the Linux operating system. And the Linux operating system is an open source operating system that allows you to do almost everything that you can do on a Windows operating system or on a Mac operating system. So that will be left for a future video. Thank you for watching.